Okay, well, welcome everyone. This is our 8th webinar on BART. We're glad you could join. Since we have a relatively small group, I'd really appreciate if you have questions, just feel free to stop me and ask. And also, if you want to use Zoom video, that's fine. You should be able to ask in both the chat and also unmute yourself. I'll go ahead and share my screen. For this, I'm going to share my full desktop because I'm going to use some external tools outside of the notebook. But and so just let me know if it's too small. But I'll start by sharing just a single browser. Can everyone see this okay?
Yeah.
Yeah? Okay, great. So we're doing webinar 8 here, and the focus of this will be on 3D Cartesian reconstruction using BART. Right now, I don't have a link to Colab because I'm using some things outside of a web browser, but we'll get that working a little bit later. There is a link to the Jupyter Notebook, but I think it's best that you follow along. I also didn't post the data yet because it's quite large. But before getting in, I wanted to go over what the plan is and a little bit of an intro. So what we wanted to show for this webinar is sort of a full processing pipeline for reconstructing 3D Cartesian data. So oftentimes we show how to use eSpirit and parallel imaging compressed sensing, but there are typically pre-processing steps that you have to do beforehand, as well as post-processing. And in many cases, the end goal is to end up with DICOM images so that you can compare it to some standard of care reconstruction method. And so what we'll do is a little bit of BART setup. We'll go through 3D pre-processing steps. We'll do a distributed 3D reconstruction since it's Cartesian. We'll do 3D post-processing steps. And unfortunately, I wasn't able to prepare the integrating the G orchestra, but that's something that we'll introduce in the future to actually create DICOMs. I did want to talk about a few updates that we've had since the last webinar. We've released version 0.9.00 as the most stable release. If you go to this link, you can see the full release notes, including who contributed. In particular, I wanted to highlight a few of the main release notes. Nick and Martin have worked on the Phantom tool to add more functionality. In particular, the Phantom can now simulate in K-space a brain phantom. So that's really useful for debugging. And it also has up to 64-channel coil. So this is really useful for more realistic simulations. Bernard and Moritz introduced a command line interface for looping and parallel processing. And we're gonna see that today when we do a distributed PIX reconstruction. And this is basically a generic way of calling BART commands, but telling it what dimensions to loop over. So this is really useful if you have a slice dimension and you want to do independent eSpirit and PIX reconstructions over that slice dimension without calling a for loop. And in particular, this also supports the message passing interface, which means that this could distribute over multiple servers and multiple GPUs if you are using those, if you have those systems. And so this really sets the stage for doing truly distributed reconstructions where slices are going off to different places. And Martin and Nick have also worked on tools for block and EPG simulations. But there are many other features, so I encourage you to check out the release notes to see the full release notes. I also wanted to mention a couple other events. One that happened recently is the ESMRM ESMRMRB MRI Together workshop, which was back in December. At the workshop, I introduced reproducible MRI reconstruction with BART. It was another webinar type presentation. And this link here will send you to the YouTube recording of the webinar. And that webinar went through the basics of BART, how to use BART, how to use it with the Phantom tool to do reconstructions, and then reconstructing 2D data from a Siemens MRI scanner with a lot of the same pre-processing steps. So that's a good that's good if you're kind of new to BART and want to see how to use the tools from first principles. And finally, for those who are attending ISMRM later this year, we'll have another secret session. The title of the secret session is Why BART? User Meeting and Hands-on Sessions. And we'll have more information to follow, but we'll have a couple of user studies, and we're looking for volunteers who might want to present their work, their research that uses BART. We'll have booths set up like last ISMRM to show particular demos, and then we'll have a discussion at the end. And so this will be Thursday, May 9th from 1 to 2 p.m. Singapore time. Any questions about this before I keep moving, or comments that people want to make, or maybe things that they would like to see at the secret session or today? Okay. All right, so I'm going to share my full desktop, and let me know if it is too small. I'll do the best I can. Can you see my screen okay?
Yes.
Yeah? Okay. Let's make this bigger. Go. All right. Okay, so going back to the landing page of webinar 8, I've just opened this Jupyter notebook here in my own web browser. So I'm running this locally. And the reason I'm running this locally is because I want to use a 3D viewer that pops out. And so I didn't integrate it with Colab. So I recommend that you just listen in this time, but please stop me if you have any questions or if you want me to run a specific command to see how it changes. So the goal of this webinar is to kind of give you a sense of what I would do if I were given 3D data and I need to reconstruct it. I have some sense of what the data represents, but I still need to understand it well. And because it's 3D, there's some visualization that needs to happen. So first, I'll just walk through setting up BART, which I've already done, as well as the viewer. We'll explore the 3D data interactively. Once we get a sense of how it's presented, we'll do some pre-processing, then we'll do the reconstruction, and finally we'll do post-processing. I want to mention that a lot of this webinar builds off of previous webinars, and in particular work that Moritz and Christian, who are online today, have prepared. Oops. Okay, so as I mentioned, BART version 0.9.00 was recently released, and we're going to use this version because we want to take advantage of the newly added looping feature. And check the announcement on our mailing list for more information about what has been released. And if you'd like to cite version 0.9.00, here's the DOI. For local usage, we've actually recently changed this, sorry, BART-Toolbox path. For local usage, we recommend setting up BART through the GitHub repository and then setting up environment variables. Just as a reminder, BART now is supported on Windows through the WSL interface, and it's supported on Mac, ARM, and Intel, and of course on Linux. And so this sort of unifies the use of BART. You can always set these path variables and use it in a Unix-like environment. Now, the simplest way to use BART is through the terminal. And we're using this Jupyter notebook just to emulate the terminal so that it's all self-contained. But of course, there are also wrapper functions. So if you prefer to use MATLAB and Python, and a lot of our users do, you're welcome to use that. And they're under the MATLAB and Python directories in BART. For today, I'm also going to use the CFL viewer that we have. If I click this link here for the CFL viewer, it will take me to our GitHub landing page, where we have this project called View. And this is an image viewer for multidimensional files that are in BART format, and it runs on Linux and Mac. It probably also would run on WSL, although we haven't tested it. And this is a useful viewer when you're working with multidimensional data, because oftentimes you want to change the dimension you're looking at. You want to slice through different indices, index to different slices. And so just plotting a single image or a single slider in Python is not always the best. And I want to emphasize that I think it's really important when you're working with data to just take a look at it and try to understand it before you start processing it a bunch. Okay, so these are just some steps for installing a fresh copy of BART, and I'm just going to go ahead and do that so that I know that I'm working with version 0.9.00 and not some experimental one from the master branch. Right here, I'm running BART on a machine that has about 120 cores. So I'm compiling BART in parallel using 16 cores. You can change this number depending on the number of CPU cores you have. Once BART is compiled, I'll add it to the path. I'll add it to my path variable. And so we have this BART-Toolbox path that will be the path that indicates where BART is downloaded and installed. And I will add it to my bash path variable so it can be found. I'll also append the Python library because this will let me use some Python functionality that I'll use in this notebook. And I will set the debug level to modestly low debug level. Christian and Moritz, maybe you can correct me. I think we also changed this to BART debug level, but it's over sort of backwards compatible. Is that right?
Yeah, I think so.
Yeah.
Christian did that.
Yes, that is correct.
Okay, let's just check that after I did this, that I have BART compiled and installed correctly. So I just downloaded it, I compiled it, I sent all of the compilation to dev null just for this demo. And indeed, I'm running here BART Webinar 8. BART is installed locally, and I'm running version 0.9. I'm also going to install the interactive CFL viewer. So I'm going to clone it from GitHub right here. And I'm going to do the same exact process. Now, it's important that you first install BART because the viewer uses some libraries from BART, and it needs to know where the BART-Toolbox path is located. So that's why I do it in these two steps. I run this. And I also made a path for my viewer installation directory, and I'm adding it to my path so that I can easily use it in the rest of the demo. And I'll just check that it is indeed installed where I think it is. So the BART viewer used in this demo is also under my Webinar 8 folder. Finally, for a small part, I am going to also plot in Python. So we have here a function that will plot a BART file in Python. So it takes in a BART file, either a file stored locally, or a Python notebook, like a Python NumPy array, where there's some options to easily change what we're looking at. But we're just going to use this very modestly, very lightly for some visualization. Okay, so now we're set up and we're ready to get started. So just some background about the data that were collected. We scanned on a GE Healthcare 3 Tesla MR750W scanner using a 12-channel head coil. When we scanned, we ran it with partial Fourier sampling of 75% in the phase encode direction. And we scanned using a Bravo sequence, which is similar to MP-RAGE on Siemens. We used a parallel imaging acceleration factor of 1.75 by 1.25. So we have this 3D data, and our goal is to, wherever we can, take advantage of steps that can be split into separate 2D problems. Some steps will naturally require 3D operations. Now, because the BART file format is simple, it's possible to read the data from many different sources. So this is by no means specific to GE. In particular, we have a BART tool called Twix Read that can directly read Siemens.dat files. And for reading GE orchestra files, such as P files and scan archives, we have a GE orchestra library called aux-BART. This is also a link to our GitHub repository on this. In the interest of time, I'm not going to go over it. I've already converted the data from a scan archive, which is what it was collected as, into BART CFL files. And so we've already converted it into this vendor neutral format. And in particular, I have two files. I have a k-space array, which is the raw k-space data, and I have a noise array, which is the noise pre-scan. One second, trying to see the participants in the chat. Cool. Okay. So again, when working with 3D data, again, I want to mention that it's really useful to get a handle on what the data looks like. And that's why, in particular, we'll be using this view tool. So the viewer will pop up a new window on my machine. For this reason, it's not directly usable in Colab out of the box. It takes some modification. So we'll skip. So for now, we don't have a Colab demonstration. Now, I'm intentionally doing everything in Bash. So I'm avoiding using Python. I'm just using this Jupyter notebook as a way of presenting. And what that means is that when I call BART commands, I'm going to be creating a lot of files. Every time I perform an FFT, I'm going to create a new BART file. Or if I do a root sum of squares, look at sampling patterns. So I'll be creating a lot of these temporary BART files that maybe I don't need them after a while. Now, in my own workflow, I like to keep these files. I like to keep them and name them something that makes clear sort of the order of operations that I'm doing. Eventually, I want to turn all of this notebook into a single script that I can give it a particular data file, and it will output the reconstruction. And in that script, I might want to delete the temporary files. But my recommendation is to keep them until you're ready to do that step. And this kind of leaves a paper trail for debugging if you get stuck, if one of the commands isn't working the way you expect. But if you are low on your own space, you can delete these files as you go. Okay, so let's go ahead and explore the data, and we'll see that we need to correct the orientation. So I saved the raw data under this folder data raw locally, and I saved the noise under data noise. And I'm just going to use BART show to see what dimensions they are. And so I'm using this bash magic to run Jupyter Notebook in bash. Okay, so we have k-space. Like all BART data, it's 16-dimensional, but truly most of those dimensions are singleton. And we see that it is 240 by 180 by 182 by 12. So indeed, there's 12 coils. And the noise data is 4096 by 1 by 1 by 12. So we're following the BART convention, where the first three dimensions are for x, y, z, or kx, ky, kz, and the next dimension is coil. And so the noise data has 4096 readout samples and 12 channels. So based on these array sizes and dimensions, we can infer that the readout is 240 samples. The phase encode dimension is 180, and the slice encode is 182, and there's 12 coils. Now, we mentioned before that this data were collected with a partial Fourier factor of 0.75, and that works out. This data was acquired at isotropic resolution, and so our phase dimension is 75% of our readout dimension. Okay, so we're working with new data. It's useful to plot it and get a sense of what's going on. So let's take a look at the raw data with this viewer and just see what it looks like. So let me know if you can't see this window that popped up. Is everyone able to see it?
Yes.
Okay, great. So this viewer is, again, included in our GitHub repositories, and it's a convenient viewer for looking at 3D data. I can click this wrench here and see all of the 16 dimensions, but you'll notice that only the first 4 have pluses. That corresponds to these first 4 dimensions that are not singleton dimensions. And right now, I'm locked in on the first two dimensions and I'm showing that as an image and we can't see much. I can go to this dimension and I can increment it, and I would hit here up to 182 or 181 with 0 indexing, and I can use this dimension, which is the channel dimension, and this will go up to dimension or index 11 because there's 12 channels. I can also window with the mouse, similar to how you would window with a DICOM viewer. I'm going to go ahead and change to the KY, KZ coordinates first. So this is now looking at KY, KZ, and the slice here indexes through different slices of the KX direction. And now I'm just going to play with the windowing and see if I'm able to find some K space. Second. Oh, there we go. So it's very faint with this viewer. Bear with me. There we go.
Maybe you can do a right click in the image. And you see its values.
Oh, the
Yeah,
values, yeah, but I
that
should be able to. It's a little bit tricky. Let me go to absolute windowing for a second here.
maybe go more in the center of K-space in frequency direction.
Okay. We can see it. Oops, lost it. So you can see the K-space data here. It's not windowed the best. It takes a little bit, because of the dynamic range of this particular K-space data set, it's a little bit hard to get right. But you can see here the K-space data. It looks like it's not fully sampled. There's a calibration region here in the center. And then the sampling pattern, because I have fractional undersampling, is not quite equispaced in the way we might usually expect. And the other thing to note is that in this phase encode direction going up down, it looks like it's cut off. The center of K-space is not quite in the center. And that's because we have a partial Fourier factor. So we'll need to account for that. Okay, I'll go ahead and close the viewer. We'll keep going. Okay, so our K-space data is not quite centered due to this partial Fourier factor. So we know that we're going to need to do some zero padding at some point. Let's also look at the data in the image domain. That's usually a useful thing to do. So I'm going to go ahead and FFT the first three dimensions, and I'll call it C image raw for coil image raw. I'm using a 7 here for the bit mask of FFT because that will pick the first three dimensions. Now, if I'm not confident at dimension counting, I can also directly pass the dimensions I want with the BART bit mask tool. I can say that I want to do an IFFT of dimensions 0, 1, and 2. That will give me the same result. And now let's go ahead and look at the coil images, and we'll play around with them a little bit. Okay, so here's the coil images. Click the wrench tool, and let's go ahead and scroll through a little bit. And it looks like we have something here. Here we go, right? So these are the coil images. This is looking through different slices. I can also look at different coils here. And so we see the coil dimensions. You might notice that some of them have more noise than others. And again, I can also look through different views of the same thing. Okay, this looks a little bit strange. It looks like there's some kind of field of view over 2 shift. And in addition, it looks like the image was flipped in the readout direction. Okay, so it's useful to know what's going on, right? It looks like we're going to need to do a little bit of pre-processing to account for the fact that the raw data that came off the scanner isn't exactly just a nice centered coil images. Okay, we'll go ahead and close this. So there are two problems in quotes, because they're not actually problems, they're just things to be aware of. First of all, the image is flipped in the readout direction, and just to follow conventions, we should probably keep things consistent by having the image in the SI direction correctly. So we'll unflip it. And we also see that there's a field of view over 2 shift in the slice encode direction. This is actually quite common with 3D GE data. When you scan on a GE scanner with 3D, they apply RF phase chopping in the slice direction, and that's what the raw data is saved as. So we'll also want to correct that. So I use BART to flip the data. I flip the first dimension 0, so this is bit mask 1 for dimension 0. And then I do FFT mod, which will multiply the case space by ±1 in whatever direction I tell it to. In this case, the slice direction, which is dimension 2. That will give me a new case space that is flipped and FFT modded. And let's go ahead and view the coil images again after doing that. So I do another IFFT to get back to new coil images. And we'll open it up, take a look. Scroll through. Okay. Now it looks like the image is in the correct orientation. If I look in the YZ directions, the phase slice direction, now the brain is no longer split by a field of view over 2 shift. You can see, though, there is aliasing in the image. And of course, there's different coil images. Some are stronger than others. Okay. All right, that's nice. The next thing we'll do is noise pre-whitening. So modern scanners should provide you with a noise pre-scan. If they don't give you a noise pre-scan, you should really check to see what you can do to get a noise pre-scan. If you can do it yourself with your own scan, because it's typically helpful for reconstruction. In this case, the scanner does give us a noise array which had 4,096 readout samples for each channel. We can use this array to build a noise pre-whitening matrix and then apply it to the data. In essence, we'll estimate the noise covariance matrix, which will be a 12 by 12 matrix because we have 12 coils. And then we'll use it to create a pre-whitening matrix and apply it to the data. And this will make the data have IID Gaussian noise in each channel and uncorrelated. To do that, we can use the BART whiten tool. The BART whiten tool has several options, but mostly we can just focus on these 3 here. It takes an input data set like case space, it takes the noise array, and then it outputs the pre-whiten matrix, the pre-whiten data. Now, optionally, we could also output the matrix that does the noise pre-whitening, the optimal combination matrix. And we can also output the covariance matrix of the data. Now, you can also have some optional arguments if you want to use your own existing whitening matrix or your own noise covariance matrix instead of estimating it from the noise data. This can be useful, for example, if the scanner provides you with its own versions of these, and you want to be consistent with some other reconstruction that the scanner does. So I'll go ahead and run noise whitening. I give it the case-based data that, remember, we flipped it and we FFT modded it. I give it the noise array. And then I create a new array that I'm going to call case-based white. This will be the new data set that I work with. I'm no longer going to be using KSP. I'll just use the whiten one. And I'll also output the optimal combination matrix and the noise covariance matrix. So we run that. And we can go ahead and plot it. And this was the noise covariance matrix before noise whitening. After noise whitening, this will be a diagonal with 1s along the diagonal. Before pre-whitening, though, this is useful to see, is our data, is there something wrong with our coil? Is it okay? Things like that. Is there a question in the chat or a Q&A? Which type of denoising method was used here? Good question. So we're not actually denoising the data. We're just pre-whitening it. What that means is that we are multiplying the data by some matrix that just mixes the channels. So we'll be left with 12 new channels, But in each channel, in each coil image, the noise will be IID white Gaussian. Beforehand, there was some noise covariance matrix, so the data were Gaussian with a particular noise covariance matrix C. And so this doesn't do any denoising explicitly, like we're not using some kind of function that tries to estimate the noise and remove it. We're basically just equalizing the channels. And so it's a non-destructive operation. You can go back to the original data if you'd like. In essence, this is explained a little bit intuitively, but you can see that there's higher noise in the second to last channel. So without noise pre-whitening, our reconstruction would be using all 12 channels equally, and we would unnecessarily amplify the noise in the reconstruction due to that channel. And so intuitively, what you can think that noise pre-whitening is doing is it's just going to lower the contribution of that channel in addition to decorrelating the channels themselves. But what it means is that I'll take the data in the 11th channel and I'll just divide by the standard deviation of the noise in that channel. And that way I lower both the noise, but I also lower the signal. So I'm just going to use less of the channel 11 in the reconstruction because it's inherently noisy. You can think of it at a very extreme. If this coil was busted and it got no signal and all it got was noise, and I knew that beforehand, then I would probably just want to remove that channel from my data. I would just take it out of my data and pretend that I have an 11 channel array. Well, noise pre-whitening does that operation automatically by using the noise variance of each channel and the covariance between the channels. Okay. So we'll continue processing the data, but now we'll just use k-space white as our k-space data because it has this noise equalization. Okay, now we saw earlier that the data were partial Fourier acquired. And so the k-space data were not centered because of this. So let's go ahead and zero pad by this factor. We'll keep doing our operations in Bash so that at the end we can turn this into a usable script. You could at this point mix Python and Bash to calculate some things. Before I do that, though, I actually want to do one more operation. Let's just look at the sampling pattern before we do the resizing. It'll be more obvious where the center of k-space is. So I'll go ahead and use the pattern command. Sorry. Okay, so BART pattern computes a sampling pattern from k-space. All it does is it just checks where the data is not equal to 0. So I'll give it k-space white as the input, and I'll call the output pat. And let's take a look at it. Okay, so here's our sampling pattern. This is in the kx, ky dimensions. You can see that ky is cut off as we expected, and here's the fully sampled center. If I scroll through slices, you'll see every few slices is equal to 0. That's because of our parallel imaging factor. I can also look in the ky, kz dimensions and better appreciate that our k-space isn't centered because it was partial Fourier. So what I'm going to do is I'm just going to zero pad the bottom of the phase encode direction to match the readout dimension. And I know that it needs to match the readout dimension because in this case, I had equal size field of view and equal size resolution. Now I'm going to calculate the dimension automatically from the data, even though I know that it's 240, because maybe in the future I'll have a k-space data set with a different size, and I want this script to be usable for future data. So I use the BART resize command. I give it the dimension I want to resize, which is dimension 1. And I want to resize it to size 240. I'm not doing it I'm not resizing from the center out. I'm just adding to the end of the array. And I'll call the output k-space white resize. So after doing this, our data now is 240 by 240 by 182 by 12. And again, notice this is just my own convention for when I'm working with BART data, that I like to just know what I'm doing. Okay, this data was whitened and resized. So that way I have like a mental note while I'm working and debugging which step of the process I'm at. I do want to show a few things though. If we look at the header file, space white resize.hdr, I'll just print it. It does show me the dimensions. It shows me the command that created the array. And it shows me what input went in and what output came out. So there is also a built-in paper trail in the arrays themselves. You don't necessarily need to rely on the file name to know where it came from. And so that's also useful for sort of recreating your steps. I can look at the sampling pattern now after doing the resizing, BART pattern, case space white resize, pat resize, and view pat resize. All right, here's my sampling pattern. We didn't sample 25% of the phase encode lines, so those are 0. And the case space center now is where it's supposed to be. The DC is in the center of my array. Okay, the next operation I'll do is coil compression, and I'm going to do it for 2 reasons. The primary reason I'm going to apply coil compression is to reduce the number of channels, which will decrease the computational complexity. Now, this data only has 12 channels, but more and more often we're seeing data collected with 64 channels or even more, and that can become quite burdensome for reconstruction time. Coil compression also has a nice benefit of removing pure noise if our data have correlation, and they almost always do. Now, here's the first real time where we're going to take advantage of the fact that my data is Cartesian in 3D. We can use the CC command to do coil compression. And typical coil compression, the most common approach is to create a matrix where we stack all of the pixels as rows and we stack all of the coils as columns, and then we perform an SVD and we keep the principal components. So that's PCA along the coil dimension. But because my data are fully sampled in the readout dimension, I can, in essence, treat each slice independently and do coil compression to each slice. Now, the reason for doing that is because I can get a higher coil compression factor, meaning I can lose less signal information if I treat each coil separately, because each coil in the in the readout direction is only going to see a small number of the actual channels. And this technique is called geometric coil compression, the GCC approach. And so this link here this will link you to the paper, but we have it built into the CC command. So we'll do coil compression in 2 steps. First, we're going to use the CC command on the case-based data just to create the coil compression matrix. Similar to the noise whitening step, this is a matrix that is non-destructive. It'll just tell us how to go from one step to the other. But next, I will use the CC apply command to actually apply the coil compression matrix to my data to a small number of channels, and this is a destructive. This will reduce the data from 12 coils down to however many virtual coils I want. And in this case, I'm going to use 6 virtual coils. First, let's just take a look at what the commands do. So CC for coil compress, it can perform coil compression directly if you pass it how many coils you want it to, how many virtual channels you want, or you can also output the compression matrix itself with the -m command. Now, it's intended to work directly in case space, so we can tell it how much of case space do we want to use to compute the coil compression matrix. And it's typical to use the calibration region for doing this, although you could use all the data if you'd like. And then we have different versions of coil compression. Like I mentioned, the typical and default is SVD. This would take the SVD of the whole data matrix. But we can also do geometric or GCC by passing this -G command. Once we have the coil compression matrix, we can use the CC apply command, which is very similar. It takes the number of virtual channels that we want, and it takes the particular input data. It takes the coil compression matrix, and it outputs the projected data. And again, it can take in different types of coil compression modes. Okay, sorry, there are a couple questions. Is there a simple way to determine the default settings for the CC command, and can you explain where to use different types of coil compression? Okay, I'll start with the second question. So when do you use different types of coil compression? I would say there's really only two ones that you should consider, either SVD or geometric. If you have 2D data, you should really just use the default SVD because you can't really take advantage of the long readout direction to get higher compression factors. If you have 3D Cartesian data, then I recommend using geometric coil compression. It basically lets you compress the data into a smaller representation without losing any information. If your data is 3D non-Cartesian, you cannot use the geometric coil compression method because the readout direction is not fully sampled. So you have no choice but to use the SVD. That means that you're going to get a less coil compression factor, which is another way of saying that the data are more efficiently, the coils are more efficiently being used, which is one reason why 3D non-Cartesian is so powerful. And so just to summarize again, 3D Cartesian, use geometric. 3D non-Cartesian, no choice, use SVD. 2D Cartesian or non-Cartesian, use SVD. Is there a simple way to determine the default settings for the CC command? Like all BART commands, there are defaults. They're not always explicitly described. Anything in a bracket is optional, and so by default will not be activated. But you're right that nothing here says, hey, the default is going to be SVD. So that's a good feedback that we're still working to improve the documentation on the tools, and so that's why we need it. Okay, if the readout is partially acquired, will GCC work? That's actually a good question. I didn't consider that. I believe that it will still work, but because there will just be a phase effect that will account for. But correct me if I'm wrong, other reconstruction experts. It should still be fine because in the readout direction, we're still fully sampled. Okay, moving on. Now, I mentioned that the CC command, you can use it in one go to coil compress data, but I like to use it in two steps. I like to use the -M command to output the matrix itself. And then I like to apply it with the CC apply command. The reason I do that is because oftentimes I'm going to distribute my slices in some way across multiple machines. And perhaps coil compression will happen after that distributed part. It really depends on the application. Or if I have an external reference data set for the ACS region, then I might want to calculate the coil compression matrix from the reference data, but then apply it to the actual acquired data. And so it's useful to have it in two different steps. Okay, so I applied coil compression. I got this coil compression matrix. Let's go ahead and print what the size of the coil compression matrix is. CC mat as well. Okay, so the coil compression matrix is 240 by 12 by 12. It's 12 by 12 because it's going to show us how to go back and forth between our virtual coils and our true coils. And there's a dimension 240 because GCC will do coil compression for each dimension separately. The coil compressed data itself now only has 6 coils, 6 virtual coils. Okay, another question. Does GCC work if the readout direction has been converted from KX to X, K space to image space? That's a great question. The answer is it depends. You can see that the CC apply command has an option to not apply the FFT in the readout. So by default, CC apply expects your data to be 3D K space. If you've already IFFT'd the readout direction into the X direction, then you should pass the -T flag so that it doesn't do a second FFT. So it won't know by default whether you're giving it data that has already been IFFT'd in the readout. You have to tell it. If I have time at the end of the webinar, I'll go over some of these things, and they actually they make a substantial difference, because you might realize that, you know, in order to do the CC command, I have to do an IFFT of the readout with -G. Then I calculate the matrix. Then I do an FFT again. And then here I do another IFFT, I do the coil compression, and then I do another FFT. So there are all these opportunities to get rid of duplicate operations if we don't need to do them in between steps. And if we're trying to make the fastest reconstruction possible, we want to get rid of these unnecessary FFTs that just are internally happening. We'll see that again with homodyne correction. But for now, I'm neglecting those. Okay, so we've coil compressed the data. We've zero padded it for partial Fourier. We have 6 virtual coils. We mentioned that the data were collected with 1.75 by 1.25 phase by slice. And again, let's just explore the data. Let's do a root sum of squares reconstruction in order to see what the data kind of looks like. So I'm going to again do an IFFT of my data, K-space, pre-whitened, reshaped, coil compressed. And I'll create a coil image of that. And then I'll do a root sum of squares along the coil dimension, which is dimension 3. That will give me a root sum of squares reconstruction, or in other words, a zero-filled reconstruction. Let's open it and take a look. Okay, I only have 3 dimensions that are active here because there's no more coil dimension. I did a root sum of squares. And here are the images. And you can probably see the aliasing. Let me window it a little bit better. So there is aliasing here that we see, right? Because it's undersampled. And I'll look also in the KY, KZ, or XY, YZ direction. By the way, just a reminder, right? We can also look at the phase if we want. Oh, sorry, there's root sum squares. Okay, phase isn't very interesting, but the viewer supports also looking at the phase of the image as well. Okay. All right, so the result's not very good. There's aliasing artifacts. You might also note that there was a slight blur in the phase encode direction due to the partial Fourier sampling. It's not the most obvious if you're just looking at a single image, but if we had a non-partial Fourier reconstruction or acquisition, and we compared the two, it would be more apparent that there's a little bit of blurring in the phase encode direction. Here, the phase encode is the up-down direction. So we'll want to account for that as well. Okay. All right, well, moving on. The last big chunk of pre-processing is getting sensitivity maps. So we'll estimate the coil sensitivities using eSpirit. Let's take a closer look at the eCalib tool. eCalib is one of the workhorses in BART for estimating coil sensitivities. It has a lot of different options, and we'll focus on a few. First, we have to give it the K-space data, and then it will output the sensitivities. Now, a useful option is the -M option. And this will output multiple sets of sensitivity maps. So if I set -M to 1, I will do what you can think of as conventional coil sensitivities. I have 1 coil sensitivity per coil. But if I set dash m to a higher number, then I'll get what are called soft sense maps. And this comes from the eSpirit paper. It's a way of accounting for inconsistencies in the sense model. Now, if you're reconstructing or acquiring, in vivo data, or especially if it's clinical, it's usually a good idea to set the number of maps to 2. And for that reason, it's actually the default in eCal. When you set the maps to 2, you're effectively going to reconstruct 2 images, and there will be some mixture of the image content. But most often, the inconsistencies that result from the sense model being violated will show up in the second map, and they can be mitigated. This might be because of motion. It might be because the scan prescription was slightly wrong for this particular subject, so that there's folding artifacts from a restricted field of view. But you don't know what it's going to be ahead of time, so you might as well account for it preemptively. Another useful one to know is this -1 command. The -1 command splits the eSpirit steps. If you're familiar with the eSpirit paper, there are effectively 2 steps to estimate the coil sensitivities. The first step estimates the noise and signal subspaces by performing an SVD of the calibration matrix that came from the ACS region. And so what this means is I'll take the 3D data, I'll take the auto calibration signal, I'll create a calibration matrix, and then I'll take the SVD of it. And then based on the threshold values, I will separate it into a signal space and noise space. The second step estimates the eigenvectors and eigenvalues by performing an eigenvalue decomposition per pixel. And these form the sensitivity maps. Now, because this is a per pixel operation, it's actually embarrassingly parallel, which means that I can independently compute step 2 for each pixel or for each slice. I don't need the data to be stored in 3D. But for step 1, I need the full ACS region of the 3D data. And so this -1 command lets us only do the step 1 of eSpirit, which requires all the 3D data. The reason being that then I can go ahead and do step 2 separately and maybe do it on multiple machines for each slice. Now there's another question. Can you perform -M2 but recon with -M1? You definitely can. You could even specify -M6, because I have 6 virtual coils, and you'll get 6 sets of sensitivity maps. And then you can use as many as you want. If you only want 1 set of sensitivity maps, then you can just index the first set. But the answer you get, the reconstruction that you get, will be no different than just doing -M1. The reconstruction only will be different if you use multiple sets of sensitivity maps in the reconstruction. But you can get all of them, and you can look at them. In fact, we can go ahead and do that as a demo. Okay, so again, the thing I want to emphasize here is that eSpirit, while it can be performed in 1 step, it can also be split into 2 steps. Step 1 requires the 3D data, but step 2 doesn't. And so if you have a setup where you're running things in parallel, perhaps it's useful to do step 1 first, and then distribute the slices and do step 2 separately. Okay, so if you're using a single machine, it's not a big deal. Just run eCalib the way you're probably used to. But again, for demonstration purposes, I will split them. So I will run eCalib with the -1 command, and I'll get an output that I'll call cal1. Okay, that was step 1. It just finished. It took the SVD of the calibration matrix that came from the ACS region, and you can see here that my output, it's 12 by 12 by 12 by 21 kernels. Okay, we're not going to focus on what the meaning of it is, but it's basically the signal space that comes out of step 1 of eSpirit. Let's make a new cell and just look at the second command, ecal2. ecal2 performs the second part of eSpirit calibration. So it has similar options to eSpirit, for example, the -m command. It needs to know what size the output should be. And then it can take the cal1 data and create sensitivity maps. Now it will run this in parallel over all of the different slices because it's embarrassingly parallel. Okay, another question is, when does eCalib-A get used? So if I scroll up, there was a -A here for automatically pick the thresholds. I'll just put a caveat that there is a small bug in this functionality, but it actually still works quite well. So -A will try to pick these two thresholds that I didn't talk about automatically. We have a sensible default for most data, so you don't have to play with it too much, but sometimes you'll get data that just doesn't have good results for the default settings, maybe because of inconsistencies or SNR levels. And so this -A will try to pick them automatically using what's called auto eSpirit. But I'm not going to use them for this demo. Okay. So ecal2, I need to tell it, oh, okay, hold on, question. For my case, the ACS region is not fully sampled. I tried eSpirit, it also works, but I want to know whether it has some bias. Okay, I think this is going to be a little bit application dependent. Is it not fully sampled in the sense that there are zeros throughout, or is there just a smaller calibration region? If it's just a smaller calibration region, then eSpirit will default to using a smaller calibration region, whatever the full extent of the fully sampled center is, and then that will change the thresholds a little bit. And if it's too small, you won't get a good estimate. If there's like a small number of corruptions, it might not be sensitive to that, and then there will be some error there. We do have a command called sake that can try to estimate them, but probably if you don't have a fully sampled calibration region, the best tool you can use is the nlinv command, which we've talked about in other webinars. BART nlinv is a way of jointly estimating image and sensitivity maps. And even though it can be used for the full reconstruction, it can also just be used as a pre-processing step to estimate the sensitivities from a low-resolution center. And so I would recommend, if you have some zeros in your ACS center, to use this command to get the sensitivity maps, as opposed to using eCalib, which could have some bias in the result. If we have time at the end, remind me and we can go over that as an example. Okay. I wanted to show here eCalib. I'm going to set the debug level to be higher, just so we can see some of the output that shows up. The output shows up after the command runs. Okay, you can see here that by default, the eCalib command extracts a 24 by 24 by 24 calibration matrix, or ACS region. I can control that with this -r cal size command. And you can see here that -r, it takes 3 values for the KX, KY, KZ calibration size. So if I have a smaller or a larger calibration window, well, BART will try to estimate it if it's smaller, but if I want to use a larger one, then I can change these values. Okay. All right. So I'm going to run ecal2. To run ecal2, I'm going to run with two sets of sensitivity maps. I'm going to tell it to make it dim0 by dim1 by dim2, which comes directly from my K-space. K-space white resize CC. It takes cal1 as an input, and the output will be the sensitivity maps. So I'll let that run, and once it's finished running, it'll pop up a window to show us the sensitivity maps. All right, here we go. So this is the first coil sensitivity map. you can see that I have 2 more dimensions active here. So this will scroll through different channels, and I have 6 of them, right? So it goes up to dimension 5. And then I also have a second set here, second set of sensitivity maps. Think though that for this particular data, there isn't much interest in there, much interesting stuff in there because this data was quite consistent. I guess the subject states still quite well. Can go here to absolute scaling just to check what's going on there. Oh. Okay, yeah, I don't see much. Okay, so most of it is contained in the first set of sensitivity maps. Okay, there was a question. Are there guidelines to choosing the size of the calibration region size? Generally, you know, the bigger the better. If you go too small, then you're not going to get a good estimate of the signal subspace. You can play with the kernel sizes a little bit as well. So this -k up here, you can change the kernel size. And of course, if it's too large, then you're sort of oversampling your data, and maybe it's better to get higher frequency samples than lower frequency. So I think it's application dependent. I would say typically, if you're doing something that's not too phase sensitive, then being 32 or smaller, like between 32 and 18 is a good rule of thumb for 3D Cartesian. So those are good questions. Okay. All right, we're finished with all the pre-processing. So what did we do? We did noise pre-whitening, we did coil compression, we did resizing of the data, and we did e-spirit sensitivity map estimation. So now we have all the pieces in place to do the actual quote-unquote reconstruction, the parallel imaging reconstruction. So the other workhorse of BART, of course, is the PIX command, parallel imaging and compressed sensing, that lets us do iterative parallel imaging reconstruction. So it solves this minimization problem. Minimize P FSX minus Y plus regularization. P is our sampling operator, which is automatically computed. F Fourier transform. S is the sensitivity operation that multiplies the image with the sensitivity maps. And it can also be multiple sets of sensitivities. X is the image we're solving for. Y is the case-based data. And R is the regularization. And lambda is the regularization weight. A common regularization is L2 regularization, or in other words, Tikhonov. And if we use that, then this defaults into the CG sense algorithm. And so for this, because our data are at a light parallel imaging acceleration, we're going to use L2 regularization, but you can change it as well. So I'm going to go ahead and print the help string of PIX. I'm also going to print the help string of -RH, which I'll explain in a sec. Now, I think that PIX, when you see it like this, it can be overwhelming in terms of its options. And that's because this truly is a workhorse tool that can do anything from standard run-of-the-mill Cartesian reconstruction to non-Cartesian with toplets, with preconditioning, with various iterative algorithms, with bases, with low memory operations, with SMS. It has lots of functionality. There's some typical functionality that you're going to use, and as you go to further, further problem sizes, then it might be useful to get to start getting into the weeds of the command. And we are working on documentation of this tool a little bit more comprehensively. We're going to use it in the most bare bones way, but I do want to bring your attention to this particular option, -R, which activates this generalized regularization option. And we can see that -RH will give us more help. And it has this kind of weird notation. So I also ran -RH. And what this does is it's an interface for specifying multiple regularizations for one reconstruction. And we have various types of regularization supported. So in general, the way that it's used is that this first option will specify what type of regularization. For example, do we want to do L2? Do we want to do L1 wavelet? Do we want to do locally low rank? Do we want to do total variation? The next option will tell us along what dimensions we want to do it. So for example, maybe for L1 wavelet, you would want to do it along the dimensions X, Y, and Z. So we would put here a flag that specifies dimensions 0, 1, and 2. The second flag lets us do joint thresholding across dimensions. For instance, if there's a time dimension, then we can handle that as a joint flag. And C is the actual regularization value. So it's a very powerful interface, and we can use multiple -Rs in one reconstruction to enforce different types of regularization. But the simplest one is L2 norm in the image domain. So if we specify Q, that'll do L2 norm. Because it's in the image domain, there are no transform flags, there are no joint flags. All we have to do is specify the regularization value. So that's what we're going to use. Now we are going to again use the fact that our data is 3D Cartesian, and we're going to get around a computational hurdle. Because the data are Cartesian, the data are fully sampled in the readout direction. And so there's really only a small benefit to performing a full 3D reconstruction at the cost of computation time. What I mean by that is that because we're fully sampled in the readout, the aliasing artifacts will be fully coherent in the readout direction. So we can't really take advantage of sparsity in that dimension, for example. We would get an SNR boost by doing it in 3D. But a 3D reconstruction will just take more computation time, especially if we have multiple machines at our disposal. So instead, we're going to do a reconstruction that is slice by slice. So what we're going to do is we're first going to do an IFFT in the readout direction to decouple the readout slices. Again, because we're fully sampled in the readout direction, we can do an IFFT there, and now we have independent slices. We'll then perform a PIX reconstruction of each slice independently and in parallel. And at the end, we'll rejoin the data into a single 3D volume. Now, before BART version 0.9, this would take some bash scripting to do. But in the new version, steps 2 and 3 are fully automated using this new looping feature. And I'll show that in a second. There is one caveat. When PIX is run, it automatically scales the data to roughly be in the range 0 to 1. The reason we do this is so that when you get a new data set, every time you scan, the dynamic range of the case-based data will differ slightly. And in some cases, if the scanner is a different scanner, it could differ substantially. But in order to make it so that the regularization parameters are roughly always the same, we scale the data to be between the range 0 and 1. That way, the regularization can be chosen in a similar way for different data sets. Now, if we reconstruct each slice separately, the scale factor will differ for each slice. Now, for a single 3D volume, maybe they won't differ that much, but it's still a different scale factor, and that just means that we'll have a different regularization value for each slice. With L2, that won't be really noticeable, but with a more advanced regularization, that could lead to inconsistencies between slices in the final result. So to have a relatively consistent regularization, we want to use the same scale factor for each slice. If I scroll back up, we can see that the PIX option has a -W, which lets us specify what scale factor we want to use. If we don't specify it, PIX will estimate it for us. We don't want it to estimate it for us because then it's going to have a different 2D scale factor for each 2D slice. But we will use it to estimate the scaling from the 3D data. Okay, so first I have to do an FFT in the readout direction. So I do inverse FFT of my data, and I'll call it case-space white resize CC FFT. So I remember that it's been inverse Fourier transformed in the readout. Now I'm going to do some bash magic to basically run PIX with 0 iterations. I'll give it the 3D data, I'll give it the sensitivity maps, and I'll give it my reconstruction, and then I'll get the scale factor. I'm going to run this for a second in a separate window just so we can see what it does. If I just run BART PIX like this, and I'm specifying a debug level of 4, then we'll get some output. Okay, first of all, we have 2 sensitivity maps. The acceleration factor is 2.55. That was the multiplication. Okay, there is a calibration region, and it scales the data by a factor of 18.47. So it divides the data by 18.47. Okay, no regularization. Oh, okay, real quick, there's a question. Can you add motion deformation fields in PIX for motion compensated image? I believe that we'll have a motion correction demo coming up at ESMM RB in September or October. So I don't believe that we can do it right now, but we are working on that. Okay, so you can see here that PIX calculated the scale factor for the 3D data, 18.47. Now I'm going to grab this scale factor and use it later down. So this command right here just outputs the scale. You can see here, sorry, I'm going to change this to RQ. All right, I get the scale factor. I set my regularization value for L2 regularization. And now I'm going to call BART. Oh, sorry, I forgot to show this. Let's just look at BART-H for a second. When I do BART-H, we can see that BART itself has some command line options. They're all optional, quite a few. And what they're useful for is for looping over dimensions. So we have this new -L or -- loop flag that lets me specify the dimensions I want to loop over. So for example, if I want to do every readout slice independently, I can call BART-L with a flag equal to 1 to loop over the readout direction. I can also do it with -P to do it in parallel. So this will activate parallel, this will reconstruct the loop dimension in parallel, depending on how many threads I want to use. I can set the number of threads with the -T command, which will run it in parallel. I also need to tell it the starting size of the loop and the end size, and I can have multiple dimensions in my flag, but if I only have one flag bitmask activated, then it's just going to be what index do I start at and what index do I end at, or I can give it a reference file to automatically do that. And finally, we can pass --MPI, and this will use the message passing interface, which lets us use multiple computers or multiple servers through the MPI, through MPI. And so this is a really useful thing for distributing the reconstruction across slices. I won't show that today. I'll just do it in parallel on my single machine. I'm also going to show a cool feature of the viewer. I'm going to open the viewer before the reconstruction ends, and what we'll get is we'll automatically get an update as it refreshes. Moritz, I have a question for you. Just to make sure I'm doing this correctly, I set the number of threads to 1 before calling the loop because I assume that the BART loop will distribute, will then run in parallel, and I don't want to run more threads than I need for each. Is that correct?
You don't need it.
You don't need it? Okay.
You don't need it. It's not nested parallelization. So if you have multiple threads on the outer loop, you just have one thread in the inner loop.
Got it. Okay. All right, so let's take that out. Good feedback. Okay, so here I'm going to call BART. I'm telling it to loop over bitmask equal 1, which is dimension 0, the readout. I give it my data as a reference size, and this is the number of threads that will run in parallel. But I'm running --loop and not --parallel loop, so it won't do that in parallel. And then I call my PIX command. So I give it the scale factor that I computed. I'm also telling it to rescale the data after the reconstruction. I give it the L2 regularization, the debug level, and then I give it the data. So let's go ahead and run this, and the reconstruction will pop up. Right here it is. So PIX is running. I'm just going to look through a little bit. Okay, you can see that I don't see the full reconstruction, but the slices are filling in as I refresh. That's because PIX is running in parallel and it's reconstructing each slice, and as it's done, it fills it in, and there, now my reconstruction is done. So I know that went pretty fast. That's because we ran PIX in parallel, and it was just parallel imaging with L2, so each reconstruction was a small number of iterations. But it's another useful feature of the viewer is that I can view the reconstruction as it happens. Again, if we have time, we can play around with this a little bit. Okay, so the reconstruction is done. We did a parallel imaging reconstruction. Let's look at it in the YZ dimension. And again, it may be hard to tell, but there is a little bit of blurring in the phase encode direction because of the partial Fourier factor. Okay, and we also have a phase. Here's the phase. Okay, you can see here also this phase singularity that we got. Okay. All right, so the reconstruction is pretty good, but there is a little bit of blurring in the phase encode direction due to the partial Fourier factor. There's also a second image because we reconstructed with two sensitivity maps. So there's really no right answer for what you do with the second image. It's kind of application dependent. In my own experience doing clinical scanning, where the second sensitivity map image may have some inconsistencies, one way of managing it is either to just throw it away or to coil combine it back to a single image and then do a root sum of squares at the end. So that's what we'll go ahead and do here. We'll combine the second map by going through the coil operator, which gets us just to coil images. And then we'll finally perform a homodyne correction on each channel independently. Finally, we'll coil combine with a root sum of squares operation to get back to a single image. Okay, so I'm going to use the fmac command, which is a fuse multiply accumulate. It's going to multiply my reconstruction with the sensitivity maps, but it's going to squash the fourth dimension, which is the maps dimension. And then I will have coil images. So let's first print what Reco L2's dimensions are. We'll do the fmac, and then we'll print Reco L2C image. So the reconstructed result had a second set of a second image reconstructed because I had two sensitivity maps. After multiplying with the sensitivity maps, I now have my 6 virtual coils, and I squashed this dimension, so I added them together. So I multiplied and accumulated. Now we have essentially multi-channel coil images. Let's take a look at them. View Reco L2C image. So I'll have 6 channels for my image data, my reconstruction. Okay, that's channel 0, channel 1, 2, 3. So there are my 6 channels. And I no longer have a maps dimension because it was squashed. All right, let's take a look at the final step we're going to do, which is homodyne correction. So homodyne is a post-processing filter that's applied to partial Fourier. You can also use PICs to directly solve for a real valued image and forego the use of homodyne. But we didn't do it here. We just did a phase-sensitive reconstruction, and then we're going to correct for the partial Fourier after the fact with a filter. So homodyne reconstruction, you need to tell it what dimension you want to do homodyne correction on. And in our case, it's the phase encode dimension or dimension 1. You tell it what fraction was homodyne partial Fourier. In our case, that's 0.75. And then you give it the data. You can also give it a different ramp filter with this value alpha, but the default alpha equals 0 is what we'll just use here. It also has some other options, which we alluded to before. If you already know you're going to go back to K-space, maybe you don't want to do all these unnecessary FFTs and IFFTs, and even doing uncentered ones just to save computation. So that's another trick to speeding up the reconstruction. But we're going to tell it to do homodyne, where our input is in the image domain. It's multi-coil, and we're going to do it for each coil independently. So I'll call BART homodyne. And then I'll finally root sum of squares the result along the coil dimension to get my final result. So we run that, and now I'll just open the two. So we have the reconstruction that came out of PIX, and we have the reconstruction that came after homodyne from the coil combined data. Let me make it bigger. Okay, they're windowed slightly differently because of the root sum of squares coil combination. Okay, and so perhaps you can appreciate that the image on the right is sharper after doing the homodyne correction. The image on the left has phase. The image on the right doesn't because it was a root sum of squares reconstruction. And I can also look at the, well, let's just explore a little bit, right? It looks pretty good. No parallel imaging artifacts. A regularization was a good choice. And I can look in the YZ direction as well. Oops. Right. So again, there is some blurring that you can see in the left image that is sharpened by the homodyne filter on the right side. Okay, so that's the last step. We went from the true raw data that came out of the scanner, and we ended up with a reconstruction that's ready to be used in some application. Now, I did intend to, but I didn't have a chance to really prepare well for it, so I didn't want to do it half finished. But I think it's also important to discuss what you do with the image after you reconstruct. If this is just for a paper, then you're probably done at this point. But if you're working with clinicians, then eventually you want to load this back in as a DICOM so that they can compare it to some other standard scan that they run. And for that, we on the GE side, again, we have integration with Orchestra, which lets you put this reconstructed image back into the pipeline that will perform gradient nonlinearity correction, Fermi filtering, zero padding, put all of the orientation to be the correct orientations, resample if necessary, and then actually have DICOMs that are usable and comparable. So that'll be the topic of another day, as well as showing how to reduce some of the extra unneeded steps if you're going to go ahead and do that. So thanks so much for listening, and happy to take questions now or show various things. Okay, there is a question about eCalib. What's the difference between using eCalib to estimate multiple sets of sensitivity maps and using the -S flag in eCalib? Okay, so they're quite different. I have to close the viewer in order to interact with this. The -S flag in eSpirit or in eCalib, if we look at what it says, creates maps with smooth transitions. Okay, perhaps it's nomenclature because I called it soft sense before. Let's go ahead and look at our sensitivity maps again. View sense. Oops, need to tell it to run in bash. You can see that the sensitivity maps have a sharp edge around them. Okay. Now hold that thought. Let's rerun eCalib, step 2, and I'll give it -S instead. And then let's view those maps that we get. The maps that we have now don't have a sharp edge. You can see that it's kind of fuzzy on the edge. And so what we did is soft sense basically tapers off the sensitivity maps so that it's not a sharp edge, because oftentimes if the thresholds aren't chosen perfectly, you might throw off some signal, or you might just have a sharp transition where there's noise. And so soft sense is actually a way of kind of mitigating that. I would actually recommend using the soft sense flag, even though I didn't in the particular demo. It's a useful thing to include. Okay. Just to clarify, when using the CC command, GCC expects KX, KY, KZ, but if you use SVD, it should be okay. No, in both cases, the command is just expecting K-space, KX, KY, KZ. If you use the GCC command, internally, it will take your data, perform an IFFT in the readout direction, and then apply SCC. If you already give it data that was IFFT'd, you can tell it, hey, don't do the extra IFFT, but it's optional. I can show that in a second if I finish this other question. Is there a Kaiser-Bessel regridding command to get 3D Cartesian K-space for easier recon, or do you need to do NUFFT and then FFT? Okay, if I understand the question is, if I have 3D non-Cartesian data, one option is to grid it into 3D data and then do a 3D reconstruction. Or do you need to use NUFFT? Is that correct? Or are you asking specifically about eCalib only? If it's okay. Yeah, so if you have 3D non-Cartesian data, I recommend using PICs in non-Cartesian mode using a trajectory and NUFFT. You'll have, even though the reconstruction will take longer, it's more accurate than first gridding your K-space data and then doing a 3D Cartesian reconstruction. So I wouldn't recommend doing it by first regridding. We do have a regridding command. We have an NUFFT command that can regrid, but I wouldn't do that as in the purpose of reconstruction.
But the question was if there's, I mean, you need to do it like you write it, like with first new FFT and then FFT. There's no simple regridding. But I'm also not sure how you would do that. Do you want to just do gridding and then what would you do with your roll-off correction, or?
Just basically trying to, for faster recon, just get to Cartesian quicker without having to go to image space first.
But I mean, then your K-space is wrong because you don't have the roll-off correction, right? Or how do I have to think about that? I mean, you have the roll-off correction always in image space, so you need the FFT and then go back. Yeah, don't know.
I just changed the PICs to do it in parallel, just so it's very quick. And it's nice to see the slices fill in. Any other questions? Now we use the soft sense maps, so there's not as sharp of a transition between the sensitivity maps here on the edges, on the boundaries. Yeah, any other questions or things you want me to just play around with to see how it affects the result? Okay, what would happen if we don't use pre-whitening? Well, we can try. In almost all cases, if you don't use pre-whitening, the result will be very subtly different. It will not be substantially different because coil design tries to make it such that the coil arrays are already quite good. the place where you'll really notice the difference is if your coil array actually has some hardware fault. Like for example, one of the channels is not operating correctly because of something broken, and it gives you just very high noise and very little signal. And in fact, like in this case, you can see that channel number 11, I guess it has a variance of roughly, 1 times 10 to the 12, whereas like channel number 0 has a variance of something closer to 1 times 10 to the 11. So it's a factor of 10 larger in variance, which is not insignificant. So will that end up affecting the result? Probably a little bit, but maybe not significantly. So one thing we could do is we could go through the steps, but essentially skip the whitening step. So we could go through all of the same processes. Let's go ahead and not do noise whitening. Now I'm going to kind of break this notebook a little bit. The first thing I want to do is I'm just going to save. I'm going to save the pre-whitened reconstruction just so we have it as a comparison point. So I'm going to use a little trick that I like to use for copying CFL files. I'm just going to flip the array, but do 0 flipping to it, so it just copies the array. So BART flip 0, Reco L2, Reco L2 white, just to save it. Oh, sorry, need to run this in Bash. Okay, that just has copied this file here. Now I'm going to skip the noise whitening step. So instead of running BART whiten, I'm just going to again flip K-space into K-space white. Skip noise pre-whitening. Pre-whitening. Right? So now I don't have a pre-whitened K-space. I just copied the data of the non-whitened K-space into the same array so that the rest of the notebook will run. Okay, so let's run the rest of the notebook. I'll skip the visualizing parts, right? Everything else is the same. We'll coil compress. The coil sensitivities. We'll run eCalib. And then we'll finally run BART pix. And I'm just going to open here Reco L2 white, so we can look at both of them at the same time. Notice that the scale factor changed. So the scale factor, if I don't pre-whiten, was 4443616. The scale factor before with noise pre-whitening was quite different. That shows why scaling the data is important before running pix, so that the regularization value is consistent, because those are very many orders of magnitude different from each other. L2. Oh, what's going on here? Still reconstructing. Check that it didn't error. Oh, still running, I guess. Oh, no, sorry, I have to close this. I messed up here, just some bash messing up. Nothing actually dramatic, but again, I want to emphasize that, using it in this way through the notebook is great for webinars, but it's not necessarily the way that I would recommend processing your data. Okay, so pix is running. These guys will pop up after the reconstruction. Okay, Reco L2, and then Reco L2 white, the original one. Okay, so here are the two reconstructions, right? Is there a significant difference? Maybe there will be on specific slices where that particular channel had more noise amplification, but it may be very, subtly different. Because in this case, the coils are not too bad, right? So I hope that answers the question. I'm happy to link to an example where there's more pathological issue that was done by Michael Hansen in a sunrise session at ISMRM that shows what really can go wrong if you don't noise pre-whiten. But as like a general rule of thumb, I would recommend noise pre-whitening because it's kind of a for free operation that only can help your data. It doesn't hurt. So I'm just looking around to see maybe the edge slices have more noise amplification in one versus the other. Yeah, not too bad. Okay, another question. Since the readout is not fully sampled, I always use 3D Recon directly rather than do IFFT first on KX, but it costs a long time. Is the parallel calculation available for this case? So this is 3D cardiac cine. Okay, so the question is, if you do homodyne in the readout direction, can you still do slice by slice reconstruction? I actually don't have experience doing that. Anyone here care to chime in? Yeah, at the risk of not giving a bad answer, I'm going to say that that's worth revisiting. But I don't think it should be an issue, but it's a good question. Okay, another question is with respect to cardiac cine, that your coil sensitivities are calculated from the diastole of the heart beating, but you use it for all the cardiac phases. Is that a problem? It kind of depends. I mean, the sensitivity maps will differ a little bit, but oftentimes it's not significant, so it's okay. You can estimate sensitivity maps that differ for each phase, and that could give you a slight improvement. It kind of depends if you're seeing problems in the first place with what you're doing. But it is common if you assume that the object itself is not changing too much and the coil loading isn't too different because of the heart beating, that the sensitivity maps are relatively consistent so that it's okay. Yeah, so is it a problem really depends if you're seeing a problem. All right. Anything else that you want to see or demo or questions? I'm just going to go back and undo my erasing of the whitening so that I don't forget. All right. I think I'll show one last thing. See if I can get it to do something useful. Okay. I just want to show how if I run a reconstruction that's a little bit more heavy, like for example, locally low ring, and I'm going to intentionally, we'll just do, doesn't really matter. I'm going to intentionally make it a bad reconstruction by using a poor regularization. I just want to show what happens as I do the reconstruction and visualize the result at the same time. So here the window pops up, the reconstruction is happening. I'm going to look in the YZ direction, go here to slice 100. Oh. Sometimes demos don't work when you do it live. Off script. Let's see what's happening here. Go L2. Okay, not doing what I was hoping for. Sorry about that. Stop. Process term. Okay, forget about the demo. Basically, I wanted to show that the viewer will update as the reconstruction is happening. But didn't get that working. Okay. All right. Are there any other questions, or do we want to stop here? So we'll go ahead and share the data so that you can run this on your own. Again, I recommend running it locally because of the fact that we're really, the goal here is to visualize the data as you work with it. And I don't think that that workflow is fully captured with a single notebook. There's some discussion in the chat that might be useful. Okay, it's talking about respiratory motion states. It can make a difference. Yeah, so it does depend a little bit on specifically on the application, but in general, the sensitivity maps change a little bit. One thing that I didn't show here is what I would call like a final result is to take all of these commands we ran and to compile it into a single bash script so that it can be run on a new data set more effectively. The notebook is useful for testing, and eventually we can move out of the notebook. But I'll go ahead and stop sharing here. So just as a reminder, well, actually, maybe I'll share my web browser one last time. I just want to mention again, for those that came in late, that we do have a couple, we have an event coming up at ISMRM. We have another secret session. So we'll do another user meeting and sort of emphasize why BART is, why BART could be useful. We are looking for volunteers who want to present at the secret session to show how they use BART for their own applications. So please let us know if you're interested. The session will be at Thursday, May 9th, 1 to 2 p.m. Singapore time. We used version 0.9.00 today in the webinar. Check it out and see all of the various highlights of the changes. Most specifically, the Phantom tool has gotten better, and the ability to loop over dimensions is now built into BART. Okay, so thanks everyone for attending. If you have any feedback, please let us know, and hope to see you at ISMRM. Okay, there's some in the chat. You can see advertisement for an ISMRM poster session on cardiac data. Would love to also have you, if anonymous participant, if you're interested in attending the secret session, please let us know, and we'd love to have you tell us about your work. Okay, thanks very much.